Hello viewers, welcome you all. So in this lecture, I am going to take up some important questions of solid state physics, and in this lecture I am taking the questions of solid state physics asked in the GATE exam, right? You can see the first question is, the valence electron do not directly determine the following property of a metal. They are asking that what property of metal is not determined by the valence electrons, right? The first option is electrical conductivity. Yes, it is determined. So option rejected. Thermal conductivity. Yes, it is determined. Option rejected. Metallic luster. Yes, it is determined. So it is rejected. Shear modulus. So shear modulus is different thing. Does not depend upon the outermost electrons, but rather it depend upon the arrangement of all the atoms inside the crystal lattice, right? Or what is the structure of the unit cell. It depend upon all these things, right? Whether it is simple cubic, body center cubic, phase center cubic, HCP, right? So it means this option does not depend. So C is the correct answer, right? Now I am going to the second question. Consider X-ray diffraction from a crystal with phase center cubic FCC, right? Lattice. The lattice plane for which no diffraction peak is observed. Now recall the concept of geometrical structure factor, right? I have told you at that time in BCS lattice. If I talk about the BCS lattice, right? In BCS lattice, right, all the reflections are present if H plus K plus L is even, right, and they are absent if they are equal to odd. But this is the case of BCC. But for FCC, right, if H, K, L are either all even or all odd, then the diffraction peak is present. But if they are mixed, I have explained you can recall that lecture. If they are mixed, I mean even odd, then that diffraction peak is absent, right? So you can see here, this is all odd, all even, all odd, and this is even odd. So this option is a correct answer. This diffraction peak will be absent because geometrical structure factor for this will be equal to 0, but for others it won't be equal to 0 because they are either all even or all odd. So this is the important question. I told you at that time that question is usually asked from a geometrical structure factor, right? Now the next question is the Hall coefficient RH. We know very well RH is equal to 1 upon NE. Here N is the density, or we can say concentration of charge carriers, and E is the charge of electron, or you can take of the hole also. We can say it is the charge of the charge carrier, and charge carrier is either electron or a hole, and they have same charge, magnitude is same, but the sign of the charge is different, either it is negative or positive. So now they are asking, it depend upon the effective charge carrier mass. No, wrong, right? The charge carrier density and the relaxation time. Charge carrier density is correct, but relaxation time has no role. The charge carrier density only, correct answer, N, right? The effective mass, wrong. So C is the correct answer, right? So usually question, although I have not covered the Hall effect in my lectures, but very well, you have learned about the Hall effect in I think BSc second year, also in electricity and magnetism in 12th class also. So we know very well, usually questions are asked from the Hall coefficient, right? So we have to remember what is the value of the Hall coefficient and what is the sign of Hall coefficient. It depends on the sign of the charge carrier. If the charge carrier is electron, it is negative. If it is hole, it is positive, right? Now let's come to the next question. The question is from a Bloch's theorem, right? Now recall what was the Bloch's theorem. Bloch's theorem was a theorem that tells us the solution of Schrödinger wave equation when the potential is periodic. And according to this theorem, the solution of the Schrödinger wave equation was psi is equal to e raised to power plus minus iota k dot r into u k into r, or you can say write x if you are considering one dimension only, right? So this was the solution, and we have learned about it. So what, look at the different options, right? Psi r is equal to u r into e raised to power iota k dot r, where u r is an arbitrary function. Wrong. U r is not arbitrary function, but u r is a function that has same periodicity as the potential, right? Here it is g, reciprocal lattice vector is involved. Wrong. Again it is wrong. Here it is correct, but here mu r is equal to mu r plus lambda, not lambda, but it is a symbol used for lattice vector, right? We can call it lambda. Lambda is a lattice vector and k is a arbitrary vector. So now this is the correct option. Here it is basically the periodicity. We usually consider it, write it as a u x is equal to u k x plus a. A is the periodicity, but they have taken periodicity as this vector, right? Lambda vector, right? So this is the correct answer. This is the definition of Bloch theorem, right? Once again I am repeating that Bloch theorem deals with the solution of the Schrödinger wave equation when the potential in which the electron is moving, it is periodic, right? Bx is equal to bx plus a, and the solution is psi is equal to e raised to power iota plus minus e raised to power plus minus iota k x, if we are considering the one dimensional case, into ukx, where ukx is equal to ukx plus a, right? But if you are taking the three dimensional case, x will be replaced by r, right? Now you can say, in an experiment involving a ferromagnetic medium, the following observations were made. Which of the following plot does not correctly represent the property of the medium, I mean ferromagnetic medium? Tc is Curie temperature. Now this graph, magnetization, this is the correct, it is hysteresis loop for ferromagnetic material, so there is nothing wrong in it, it is correct, right? If I talk about this is the magnetization versus temperature graph of a ferromagnetic material. What they have plotted is 1 by t, so it is now inverted. If they have plotted it versus t, then it would have opposite shape. But you can see, as the temperature is increasing, right, then 1 upon t will be decreasing. You can say that temperature is increasing toward this side, right? Temperature is increasing toward this side, but if you are going toward this side, it is decreasing. So when you are going from here toward this side, I mean decreasing temperature, right? Then at temperature T is equal to Tc, right? They are taking it 1 upon Tc. What you will get? You will get the spontaneous magnetization. But if the temperature is greater than this Tc, once again I am saying that the temperature is increasing in this direction because it is 1 upon T, and it is decreasing in this direction, right? So if you are going toward this side, no spontaneous magnetization because temperature T is greater than Tc. If you are going toward this side, right, the temperature T is less than Tc, right, and you are getting a spontaneous magnetization, right? Now, so this graph is again correct, right? If you come across this graph, now recall the graph of anti-ferromagnetic and ferrimagnetic material. So this graph is quite similar to that graph. So it means this graph is not linked to the ferromagnetic material, right? Because it is a graph of anti-ferromagnetic material, right? So this option is wrong. As far as this graph is concerned, specific heat versus temperature, it is also correct for ferromagnetic materials, right? Now, the thermal conductivity of a given material reduces when it undergoes a transition from normal state to superconducting state. So what is the reason? So I have although covered the superconductivity topic, but I think the thermal conductivity concept was not covered. So I want to tell you the thermal conductivity of a material, when it goes from normal to superconducting state, it usually get reduced. Thermal conductivity is reduced, and this is because when the electron are involved in the superconducting process, they are not going to take the heat, right, for thermal conductivity, right. So this is the reason, right. So let's look at the different options. And the Cooper pair cannot transfer energy. This is wrong. Upon the formation of Cooper pair, the lattice becomes less. Again, it is wrong. The electron in the normal state lose their ability. They are calling normal state, right? Not superconducting state. Lose their ability to transfer heat because of their coupling. Again, it is wrong. The heat capacity increase on transition to the superconducting state, leading to a reduction in thermal. Heat capacity is increased. That is the reason. Heat capacity means the amount of heat required to raise the temperature. It is increased because now electrons are not participating. Only lattice part is participating, right? So this is the correct answer, and you have to remember this concept of thermal conductivity, that the superconducting state has a low thermal conductivity, right, as compared to the normal conductor. And the reason is non-participation of electron in this process, right? Sorry. So now I'm going to the next question. So you can see here, the question is the temperature dependence of magnetic susceptibility of a ferromagnetic. We know zeta is equal to T upon C upon T minus theta or Tc. So what is the correct answer? B is the correct answer for T greater than Tc. This is very important, right? I have told you that T is, in normally or in normal situations, T is always greater than Tc because Tc is very, very low. Only this relation is valid. If T becomes less than Tc, then this will become negative, right? So this is not possible. This is not going to happen for ferromagnetic materials. So this relation, Curie-West law, it is valid for a T greater than a Tc, right? And this is wrong, right? This is again wrong. Plus sign is not there. So this is for ferromagnetic material, Tc is the Curie temperature, but the requirement is T should be greater than Tc, right? So B is the correct answer. The order of the magnitude of the energy gap of a typical superconductor. I have told you that the energy of the Cooper pair, electron-electron pair, it is of the order of 10 raised to power minus 3 electron volt, right? So I have told you. So they are asking the same question, the order of the magnitude of the energy gap, because energy gap is equivalent to the energy required for forming a Cooper pair, right? We have to understand it, because energy gap means that energy must be supplied, right, to the electrons so that they couple together each other and form together with each other and form a Cooper pair. So the energy of the Cooper pair is of the order of 10 raised to power minus 3 electron volt, means 1 milli electron volt, not mega, it is given here. So D is the correct answer, right? So I have explained you in that lecture, right? Now the next question is, for a three-dimensional crystal having n primitive unit cells with basis of p atoms. Now, although this question has been not covered, but you have to remember that in this situation, the number of optical branches are linked with the number of atoms in the basis as this formula, 3p minus 3, right? Now, I am going to the next question. For an intrinsic semiconductor, pure semiconductor, Me star and Mh star are the mass of hole and electron near the corresponding band edges. At a finite temperature, the position of the Fermi level, we know very well that the position of Fermi level depend upon both the mass of electron as well as hole, right? So C is the correct answer, right? It does not happen that it depend only on one factor. It depend upon both electron as well as hole. So now I am going to the next question, and the question is, the metal with body center cubic BCC structure shows the first diffraction peak at Bragg angle theta is equal to 30 degree. The wavelength of the X-ray used is this. The volume of the primitive unit cell they are asking. Primitive unit cell volume means volume divided by number of atoms, right? This is the volume of primitive cell. Primitive cell volume is the volume per unit atom, we can say. So volume means A cube, number of atoms for VCC structure 2. So we have to first of all find the value of A, then by using this relation A cube by 2, I can calculate the volume of the primitive unit cell. But for it, I have to use Bragg's law. 2d sine theta is equal to n is 1 given first lambda, right? So and d theta is 30 degree. What about d? D we know very well, d is equal to A upon h square plus k square plus l square. Now here I want to tell you one thing, that they are saying a metal with body center cubic structure show the first diffraction peak. Now the first diffraction peak for BCC structure occur for HK value 110, and for simple cubic it occur at 100, and for FCC it occur at 111. So we have to remember these three values of HKL for simple cubic, body center cubic and face center cubic. These are the values for observing HKL, for observing first diffraction peak. So by using this, I can now find the value of D. So D will become 1 plus 1 plus 0 AY under root 2. So I can put here value. You can see here the simplification. 2d sine theta is equal to n lambda. D is equal to this, right? Diffraction peak occur for this plane. Now D is equal to AY under root 2 from here, right? So I am putting the value of D here. So I get 2 into AY under root 2 sine 30 degrees equal to lambda. Now putting the value of lambda is given 2.1 angstrom, right? Here you can see, right? So when you put the value of lambda, you will ultimately get the value of A. So the value of the A is calculated as this one, that comes out to be this one. Now the volume is A cube divided by 2. So it is calculated here. It comes out to be 13.1 angstrom cube. You can see here the correct answer is B. So here the thing that we have to remember, two things are important. One is they are asking about the volume of the primitive unit cell. Primitive unit cell volume is volume per unit atom. So here the number of atoms are 2. So we have to divide the volume A cube by the number of atoms means 2. If the structure was FCC, then we have to divide it by 4, right? But simple cubic, it is A cube divided by 1, so we can say A cube. And the another important point is the first diffraction peak. For simple cubic, HKL 100, body center cubic 110, and face center cubic 111, right? So this was the next question. Now I am going to the next question. You can see for an ideal Fermi gas in 3 dimensions, the electron velocity Bf at the Fermi surface. So recall the relation for a Fermi velocity. I mean the velocity of the electron at Fermi level, and we know very well that it is directly proportional to n power 1 by 3. So D is the correct answer. So we have to remember this expression, so you can drive it, right? Now I am going to some another questions, right? A fast force doped silicon semiconductor is heated from 100 degrees Celsius to 200 degrees Celsius. Which of the following statement is correct? Position of Fermi level moves toward conduction band, towards dopant level toward conduction lab. Position of Fermi level moves toward the middle of energy gap, right? Position of dopant level. Now it is very important that in doped semiconductors, right, whether it is N type or P type, they are giving all these conditions, but we have to focus on the important property of the Fermi level for the extrinsic semiconductor or doped semiconductor. We know very well in doped semiconductors, the position of the Fermi level depend upon the doping. Either it is close to the bottom of conduction band, or it is close to the top of a balanced band. But in both the situations, if the semiconductor is heated, then it moves toward the center of the or middle of the gap, forbidden gap. So C is the correct answer, right? Now the next question is, consider the BCS theory of superconductors. Which one of the following statement is correct, right? Now presence of energy gap at temperature below critical temperature. Not correct. They are asking not correct. Sorry. Presence of energy gap at temperature. So it is true, because we know very well the energy gap of the order of 10 raised to power minus 3 electron volt exists, and that energy is required to form the Cooper pair, right? Different critical temperature for different isotope, again correct, because critical temperature inversely proportional to 1 upon under root m, right? Quantization of magnetic flux in superconducting ring in the unit of this, right? Now I will come to it. Presence of Meissner effect. It is also correct. We know very well that Meissner effect is very, very important property of all the superconductors, right? They show Meissner effect, right? Now I am coming to this one, quantization of magnetic flux, right? So if I come to this, I think I forget to tell you about this in my lecture on superconductivity. So when a superconductor is placed in magnetic field, right, and its temperature is lower to the critical temperature, we know very well it will become a superconductor, right, and the entire magnetic field is pushed away from it, right? Now in that situation, a persistent current is developed inside the superconductor, right, that keep on flowing, and it will produce its own magnetic field or own magnetic flux, right? And that magnetic flux phi is given as n into h upon 2e, right? Here h upon 2e, right, this is called flux quantum or fluxoid, right? This is very, very important. H upon 2e. Flux quantum means quantum of this flux, and n is equal to 1, 2, 3. Means this flux is quantized, right? When a material goes from normal state to superconducting state, and when its magnetic, the applied magnetic field is switched off, right, removed, then a persistent magnetic field or magnetic flux is developed inside that is quantized, and the quantum of that flux is represented as h upon 2e. So here it is e, should be 2, so it is wrong, right? So you have to remember this, quantization of flux in the superconducting state. Quantization of which flux? Magnetic flux, right? So this is all about this question. So in this lecture, I have taken up a few questions, not so many questions, to recall all those important things that I have covered in this course of solid state physics. So I'm hopeful that the things are clear, right? Now in the next lecture I will start a new topic. So thank you very much.